All right, so we looked at this set of parametric equations. We ended up graphing them on our calculator. We did all kinds of things. So let's get our notes back out. Let's turn to page 18. And let's do it again. So we're going to repeat the exact problem, type of problem, for these two parametric equations. The first problem says to find the points determined by these t values. So in other words, we're on page 18, problem number 5, on the bottom. We are going to figure out what the x and y ordered pairs are for each of these t values. Well, guys, is this hard or confusing? No, right? Because all we have to do is plug in t. So if we plug in -3, we get -6 for x and -10 for y. Right? Okay, well, let's go. Go ahead. I don't need to talk. You can do this. Plug in -2 and -1. And so on. Look okay? Now I'm going to skip to C because since I have my points, it says sketch it by hand. And since I have my points, I'll just go ahead and sketch it by hand. This is letter C. We'll come back and do the other parts. I am not using, obviously not using graph paper, but mine looks an awful lot like a line. Does yours look like a line? Well, let's check that. Because part B says, find the direct algebraic relationship between x and y by eliminating the parameter. I can't remember how we did this the other day. But what occurs to me at this moment is eliminating the parameter means getting rid of t. So I could multiply my whole top equation by -3 and my whole bottom equation by 2. And won't that eliminate the parameter? Together. So I have -3x plus 2y equals -2. Now, is that the way I did it the other day, or did I substitute? Anybody remember? You could also substitute out the t's. Here I eliminated them. Is everybody following here what's happening? So the directions specifically said, eliminate the parameter. T is the parameter. So if I am to eliminate the parameter, I said, okay, that's what I'll do. I'll make one -6 and one +6, add them together and they're gone. That leaves me with -3x plus 2y equals -2. Is this the equation of a line? Yes. Could you get that in y equals mx plus b form? Yes. You don't need to, but clearly you could, so that is a line. This line right here. All right. Now, let's review how to do that on our calculator, because the last part of that question says sketch on your calculator. So, anybody remember what we need to do in order to sketch parametric equations on the calculator? Bobby?
Don't you go on mode?
Yep, you go to mode, so press mode on your calculator, and then click down to parametric. Some of them actually say parametric, some of them say PAR, parametric mode. Now, I have no idea how your window is set. So if I were you, I would just set it up standardly. So I would say go to window, and then T-min, I would just make all the mins -10 and all the maxes +10. I wouldn't change anything else. All the mins, -10, all the maxes +10.
If we do zoom standard for that, does it keep it?
I don't know what it does to the t's. It'll fix the x's and y's. I'm not sure what it tries to see.
It
What-
gets 360 on the T max.
Yeah, so T is often an angle,
Okay.
and so it's setting it up from 0 to 360 probably. So you'll want to manually do that. 0 to 360 won't work in this problem, so you'll manually want to fix it. It'll probably take care of the x's and y's. All right, so all my mins are -10 t x y, -10. All my maxes t x y are +10. Now I'm going to y equals, and I'm going to put in these two equations. So I'm going to put in 2t, and remember, the variable button is t now. Where you used to get x, you now get t. And then y is 3t minus 1. And hit graph. Did you get a line that looks kind of like mine? Only nicer? Okay, now remember, your calculator is set in parametric mode. So if you're trying to graph something regular, not gonna work. You're gonna have to change it back to function mode. So you can do that right now if you want, or just remember later on that it isn't going to graph right because it's in parametric mode. All right, so we did one of these the other day. We just did a second one. I'm gonna erase all this now. We're moving on to something different. Any last minute questions about building the T-chart? That's easy. Plug it in. Plotting those points is easy. Connect the dots. Eliminating the parameter. So direct algebraic relationship between x and y means write an equation that has just x's and y's. So we got rid of the parameter, t. And then we sketched these two equations on our calculator. All right, you think you got a grip on it? All right, so now there's one more thing, and then this section will be finished. It says sketch the inverse. Now, what I would like for you to do, did we do this already? No, we didn't do this already. What I would like for you to do, if you don't mind, is, here's the original. Would you label, right on your paper here, just label all of the original points. So this is -2, 0, -1, 1, 0, 0, 1, -1, 2, -1, and 3, 0. So you know how to label points, just label them. Any wild guess how I'm going to graph the inverse? Nyla? Exactly. Remember when we were writing the equations, guys? Remember how we flipped the x and y? You're going to do exactly the same thing, only you're flipping the points. So instead of graphing -2, 0, you're going to graph 0, -2. And 1, -1. And 0, 0 won't change. And then -1, 1, -1, 2, and 0, 3. This is a picture of the inverse. And if you think about it, hopefully that makes perfectly good sense to you. Because the original was kind of oriented on the x-axis. The inverse then will be oriented on the y-axis, because when we do inverses, we switch the ordered pairs. Right? All right, you try the second one on your own. Try B on your own. Everybody okay? Did you get that one graphed okay? Everybody? Okay, how do we graph? If I give you a picture and say graph the inverse, easy. All you have to do is take the original ordered pairs and switch them. Flip them. Y and X. That's how we do inverses. Always. Whether it's equations or points or whatever. Got it? Okay. So now, okay, so 1-5 finished. That homework will be due on Thursday. So get that done. That shouldn't be too hard. And now we're going to talk about, this is what you need your graph paper for, I think. I left room in the notes, but I think it's going to be easier for you to do this on graph paper. So here's, it doesn't matter to me though, it's up to you. Here's the original picture. I'm going to graph it real quick. That is called f of x. So this is your original function right there. What we are now going to do is change that picture. So we have to make sure we know the impact of putting numbers in various places in the problem. Now, this one, I am completely confident you know. This is letter B. You should know what impact adding 1 directly to the x does. When you put that x plus 1 in parentheses, what does that do to your picture?
Left.
It goes left 1. So you're simply going to redraw that exact picture 1 unit to the left. Now, some kids like to, remember the squiggly line we used on our piecewise functions? Some kids like to put a squiggly line in there, left 1, moved it over 1. And then this line is now over here. So you can, see what I'm doing? I'm drawing my shape using this line as a reference point, only now it's over here. If that confuses you, then move every point. So take this point right here, which is left 2, make it left 3. This one is left 1, make it left 2. Move every point 1 unit to the left, individually or as a whole if you want to do it this way. So that's letter B. That's my shape moved 1 unit to the left. So you were doing that before with like absolute values and parabolas and stuff. Now you're just doing it with some random generic shape. So a surefire way to do it, if you're all confused, is to move each individual point. So instead of left 2 down 3, go left 3 down 3. Instead of left 1, go left 2. Just move every point 1 unit to the left. Okay. I don't think we've talked about this, have we? What does a coefficient out in front do? We know if we add or subtract, but what does a multiplier do? Well, a multiplier changes the size of the picture. We didn't change the side here. We just literally picked it up and moved it over 1. This number in this position multiplies the height of the picture. So it doesn't shift it at all, it just stretches it. So go back to the original. What does that mean about this point right here now? Everything's twice as high as it was. So isn't this going to be up here now? Twice, up 2 times, up 2 steps. And now that guy looks like that. He's taller. And then this point, if I copied this right, was originally down 3. So now he's going to be down 6. So he's still left 2, but now he's down 6. This guy is going to be down 4. And that one's going to be up 4. A coefficient, a multiplier out in front, double, or not double, multiplies the vertical. So in this case, it was a 2, so it doubled the up and down, the vertical. Gotta remember that, okay? Gotta remember that a number out in front does that. All right. Still using that picture. What do you think what's going on here? What change is that making? Upside down. The negative out in front is an upside down. We talked about that, guys. Put a negative in front of an x squared. Doesn't that turn your parabola upside down? Turns anything upside down. Whatever the shape is, a negative out in front is going to turn it upside down. Which means that instead of this point, look at the original, instead of this point being 3 down, he's now going to be 3 up. So I've got this so far. There he is. Upside down. A negative out in front turns you upside down. Okay, so lots to keep track of. I'm gonna pile it on. Look at problems D and E. Do you see how they're different? D is the absolute value of the whole thing, and E is just the absolute value of X. You can think of this any way you want. I like to think about the absolute value of the whole thing. I think of as bottoms up. Because when you take the absolute value of positive things, they don't change. But when you take the absolute value of negative things, they become positive. So anything in the original picture that's negative, and that means under the x-axis, these are negatives. Anything red is going to go up. The bottom of the picture goes up. Anything that's still black just stays there. Bottoms up. You bring the bottom up and leave the top unchanged. So when I graph that, anything that's black is staying the same. So that's staying the same, and this is staying the same. But this little parabola looking thing, he's got to go up because I'm taking the absolute value of him, so he's got to go up. And this little guy shooting down here, he's got to go up. There is a picture of the absolute value of the whole function. Anything below, anything on the bottom of the picture has to come up. So this has to come up, and this has to come up. All right. Everybody got that? Haven't memorized it yet, but you got a good note there taken, so you know that's what happens when you take the absolute value of the whole thing. Now, what happens take the absolute value of just the x. Well, this one is wild and wacky. All right, so here's what I want you to do. When it's the absolute value of just x, I want you to draw the right side of the picture. So, draw that. So, point here, point here, point down here and up here. So I have drawn the right side of the picture. Everybody okay with that? That's step one. Step two, and then only 2 steps. Mirror right onto left. So in other words, take this picture right here and mirror it onto the other side. So this exact picture is going to get mirrored over to here. So it's going to be down like this, and up like this. And that's the answer. When you draw the absolute value of just x, you draw whatever's on the right side of the picture, whatever it is, you draw it. And then you mirror that over onto the left. Now, somebody's probably thinking, Mrs. Ford, well, what happens to the stuff that was originally on the left? It's gone. It's gone. That doesn't have a place in this problem. We draw, when we have a problem that looks like this, we draw the right side and mirror it onto the left. All right. Now we have a new picture. We're going to do some stuff with this new picture. So, who can tell me in words what is happening in this problem? There's 2 changes being made. What are those 2 changes? Can anybody tell me? All right, just a second. Let me catch up to you here in a minute. I'm just throwing my shaker. What did you say?
Is it up to and upside down?
It's definitely up to. No question about it. Negatives always mean flips. But there's a difference between a negative outside, that's upside down. That's upside down. A negative inside is a flip, but it's not a flip this way, it's a flip this way. So this is a sideways flip. Oh my gosh, Mrs. Ford, there's so much to remember. I know there is. There just is. Just gotta remember it. A negative inside on the x, a negative on the x, is a sideways flip. So this picture is flipping sideways and going up 2. Now, if it helps you, you're going up 2. So whatever you draw is now sitting up here instead of on the x-axis, right? Up 2. And what you're drawing is the left is going to the right and the right is going to the left. So let's start with this little triangle right here. Because just that little triangle. What happens when I flip him left and right? He just stays the same, doesn't he? So I'm just going to draw him, but I'm gonna draw him up here like this. Does that make sense to you? And then this, I don't know, half trapezoid thing, he's shooting off to the right, so I'll have to have him shooting off to the left. And then this little triangle will be sitting right here. Did we move everything up to and flip it side to side? Develop your own strategy. You do not have to do it the way I just did it. You don't have to do it that way, but end up with that picture. Uh-oh. What do you think this means? Be careful. Earlier, we talked about a number out in front, right? And what did we say a number out in front did?
Stretches the height.
So it multiplies the height. So actually, if it's a 1/2, it actually won't be a stretch, it'll actually be a shrink. But depending on the number, it's either a stretch or a shrink vertically. That number multiplies the height. This number, hold on to your hats, divides the width. This is probably the single biggest, trickiest part. A coefficient on x divides. It divides. So in other words, when I look at, I'm just gonna start with this trapezoid, or triangle right here. How wide is he right now? He's too wide. He's gonna get divided by a half. What does that mean? Divided by a half, that's multiplying by 2, isn't it? So now that triangle is actually 4 wide. Your horizontals get divided by a half, which happens to be multiplied by 2. So this little triangle that's over here on the left side is now also 4 wide. So think of every hash mark as being doubled. So we're twice as wide as we were. Every width is twice, because this number divides the width. All right, tell me what's happening in problem C. You know, what is taking the absolute value of the whole thing do? Bottoms up. What is tacking a +1 on the end of 1. And go back to the original picture. Everything on the bottom is going to come up. Everything on the top is staying up. Now, I'm not done yet. I'm not done. But would you agree that that is bottoms up? Now I'm going to take the whole thing and move it up 1. So this time I didn't do my squiggly line. I don't know if you want to do that or not. Some kids it helps, some kids it confuses. Do whatever works for you. I'm just literally going to pick every point up 1 unit. And the blue thing is the answer to the question. Feel free to use colored pencils and do that strategy if that works for you. Okay? Everybody okay with that? Get both steps there? All right, tell me what's happening in this one. What's that do? It's going to go upside down. What's this? This is the tricky one. This is where we draw right and mirror left. Oh, I don't know how you want to say that. Maybe you don't want to write it at all. I don't know. So we draw the right side and mirror onto the left side. I'm going to do that first. I'm going to do this in 2 steps. If you want to do it in 1, go for it. I'm going to do it in 2. So I'm going to draw the right side, so draw it exactly as it appears. There's the right side of the picture. Now I'm going to draw that exact same thing on the left. That is this part right here. Okay. Now I gotta flip it upside down, which simply means exactly that, upside down. So the blue is the answer, and since it's easy for me to erase, I'll go ahead and avoid the confusion. But you are allowed to do what I just did, and if I'm using a different color, it's fine. It's fine. That's the answer. Everybody okay with that? I'm going to make your day. 1.6 is also due on Thursday. I knew that would make you very happy and excited. And for our next class, is that tomorrow? I'm going to prepare a little just kind of quick review, and we're going to move on today. But tomorrow we'll start class with a little kind of, I'll give you a shape, and then we'll come up to the board and graph a few variations of it, because it's a lot. It's a lot. Remember, pluses and minuses move us sideways, up and down. Multipliers affect our size vertically or horizontal. Negatives flip us one way or the other, depending on where they are. And absolute value just does weird things, right? So we just have to know. Okay? All right. Let's move on to 1.7 then, which is going to absolutely make your day. This is all word problems. Okay, so we're going to start. Don't ever say that I'm not multidisciplinary. Area here. Get out a sheet of paper. We're going to do a little craft. Arts and crafts. Scrap paper. Scrap paper. Do not use my graph paper. You use scrap paper. If you do not have any scrap paper, grab a piece of notebook paper over here. And we are going to do something sort of fun. All right, here is what I want you to do. Y'all got a piece of paper? No, we don't have a ton of time to do this. And we're not measuring and cutting, but we're like, this is just, we're doing this quickly as an approximation. All right, so everybody's got a piece of paper. Pretty much the same size. We're all using pretty much the same size paper. All right, here's what I want you to do. I want you to, all right, I want you to tear a square, and it can be any size square you want, out of each corner. So just rip a square out of each corner. Now, like my square is this big. You pick your own size. I don't want them all to be the same. But that's the size I'm going to take out of every corner. So we want our corners that we're ripping out to be approximately the same size. You're not getting graded on your craft here, folks. This is like kindergarten. Everybody's is perfect. All right, so you got the corners all ripped out. Over there. You can use this. Oh, I see what you're saying. Yeah, it's the quality stuff.
Yeah.
All right, once you get your corners ripped out, I want you to fold up these flaps. See how you created flaps? Fold them up like this. Fold up all the flaps. And you have created a little box. Okay? So fold up your flaps, you created a little box. All right? Now, I want you to look at something. Kendall and I started with the same size piece of paper. Kendall's box looks like this, and my box looks like this. And your box probably looks even different than those two. So here's the deal. If I were a really nice teacher and I had a huge bag of M&Ms and I walked around the room and I started filling your box with M&Ms, would everybody's box have the same number of M&Ms? No. Some of the boxes are going to hold more M&Ms than other ones, right? We call that volume. The volume of my box is different than the volume of Kendall's box, is different than the volume of Emma's box. What made a difference? We all started with the same size paper. What's different? What we took out. So, you didn't know it when we started this wonderful little craft project, but you are doing one of the, if not probably the most famous pre-calculus problem in the world. Every kid in the whole world in pre-calculus has this problem. You have a piece of paper. This one happens to be 12 by 15 in the middle. We cut corners out. We don't know how big those corners were, but we know that the size of them determined the volume of the box. Ultimately, the size that I cut out determined how much my box would hold. Your job is to maximize the volume of the box. So in other words, take that piece of paper that's 12 by 15, cut out the corners, and make that box hold as most M&Ms as it possibly can. Okay? All right. How do we find the volume of a box? What's the formula for the volume of what we call a rectangular solid? Length times width times height. Now, I want you to go back to your box, back to my picture. The original length of the paper was 15. But remember, we chopped this off and this off. So now the paper is only this wide or this long. How would I express that? 15 minus 2x. The width of the paper used to be 12. So 12 minus 2x, you okay with that? Now, what about the height of the paper? Remember, you folded these up. You folded these up. How tall is my box? X. And that is the formula for the volume. Now, you don't need to multiply that out. Don't multiply that out. Now, we want to find the maximum volume. So we're going to graph that on our calculator, and it's going to have some kind of weird shape. But won't the maximum be the top of the hill, wherever that happens to be? There's one more thing we have to talk about before we graph it, though. Notice in the notes, what was the first thing I asked you? Domain. We got to get that down, okay? You know this. I think we talked about it before. If I am going to cut off a piece here and a piece here, and it's only 12 to start with, what is the most I can cut off from each side? 6. So your domain, the highest value is 6. And of course the lowest value is 0 because you can't cut a negative piece off. Now notice, I didn't use this dimension. Here, the smallest I could cut, or excuse me, the biggest I could cut off would be 7.5. But I can't do 7.5 on this side, so I always look at the smallest dimension. Always look at the smallest dimension. And half of that is the high point of your domain. So when you go to graph this on your calculator, by the way, we're in parametric mode, so we need to switch that. It ain't gonna work if you don't switch it. When you go to window, X min must be 0 and X max must be 6. I say that because if you graph the entire picture, this whole thing, you'll find another maximum, but it won't count because it'll be bigger than 6, okay? So set your domain right from the beginning so that you see only the thing you want to see. Y min, 0. Y is the volume, guys. So here's X min, X max. Y min is always going to be 0 in one of these problems. And then Y max is actually the answer, which we don't know. So I'm going to pick a number for Y max, like 200. Random guess. Now I'm going to type in my equation with the parentheses. And hit graph. Oh, I guess well. Can I see the top of my hill? Now, sometimes when I guess I'm not so good, and so I don't see the top, so then I have to go back and pick a bigger number, like 300. Does that make sense to you? All right, let's find the maximum. Second, calc, max, left bound, right bound, yes, that point was 2.21, comma, 177.23. I rounded off, obviously. 2.21 and 177.23. You match that? So now we're going to answer the question. The question was, what is the maximum volume? Okay, what is the maximum volume? 177.23 cubic inches. Tell me what this 2.21 represents. What's that? That's the amount I cut off. That's the size of my corners, right? That size corners will give you this volume, which is the biggest volume you can have. Wow. All right, you guys are impressive. Would you make sure your boxes get put in the recycle thing? If you have any spare scrap corners, make sure they get in there too.